Here's a projectile motion problem where you have an angled launch with a changing elevation. In this example problem, Phil Mickelson hits a sand shot from the bunker, which is 3.2 meters below the hole. The ball leaves the club with a speed of 15 meters per second at an angle of 70 degrees above horizontal. If it lands in the hole without a bounce, how long was the ball in the air? At what angle did the ball strike the cup? Let's start by drawing a picture. Here's my green, and here's the cup, and we'll put a little flag stick in there. And down below, you've got Phil Mickelson, and he's perched over his ball, and he's going to strike the ball, and it's going to leave at a pretty steep angle. We'll move him over to make a little bit of room so we can see this object. It's leaving with a velocity of 15 meters per second, and the angle it makes is 70 degrees, pretty steep. And this ball is going to move along a parabolic trajectory. It's going to curve, and it's going to land right in the hole. And what we know is the elevation of the hole changes by 3.2 meters. So the height here is 3.2 meters. They don't say anything about the horizontal distance, but it doesn't appear that we're going to need that. We'll see what we need as we set up the problem. So I've got a picture. I think I have a grasp of what's going on. And let's set up an XY table because we want to look at how this object's position is changing in both directions and use both sides to hopefully relate the pieces we need. So in the x direction, you have the acceleration in the x, which is always 0 meters per second squared. There's some time at which the ball is going to be in the air. There's the velocity at which it leaves in the x direction horizontally, which is not 15 because 15 is at an angle that isn't in the x or y direction. There's x, there's the positive y as a reference. That is at an angle, so it doesn't fit into my x or y side. I have an initial position in the x, let's call that 0, and a final position in the x, which I don't know. All right, and that would be, along this way. If I were to draw, this would be some x final position, and here's our x initial, we'll call 0. So that's always a good rule of thumb. And if you move vertically, you have your y's going that way. Let's look at the y side. In the y side, you have the acceleration of the y, which is always negative 9.8 meters per second squared. You have some time the ball's in the air, which is what we're trying to find in the first part. You have an initial velocity in the y, which is the vertical component of that initial velocity. Some final velocity, which we don't know. Initial position in the y, let's call on the ground y initial equals 0, which means up here would be y final is equal to 3.2 meters. That would account for the change in position. It's always good practice to call the lowest point on your picture 0. It'll make your math a little bit easier. So we'll call y final 3.2 meters. Now, we don't have enough information yet, but we do know the angle and the velocity that this object leaves. So I'm going to set up and look at this and look at my component velocities. This is going to have a component in the x direction and a component of that velocity that's in the y direction. And using our trig, we have a right triangle, and we have an angle. We have, if I'm trying to find the y direction, we have an opposite leg to that angle, and we have a hypotenuse. And we know that SOHCAHTOA, S-O-H, sine of an angle is equal to the opposite over the hypotenuse, which in this case, we have that opposite is VIY, and the hypotenuse is the velocity we have. And so if I do a little algebra, VIY is going to always equal V sine of the angle theta, which in this case is going to be 15 sine 70 degrees. And in my calculator, make sure I'm in degree mode. If I go into mode, I'm still in degree. I have 15 sine 70, which would be 14.1 meters per second. And let's do the same thing in the x direction. Now, x direction is my adjacent side, and I know that cosine of theta equals adjacent over the hypotenuse. And my adjacent side would be my Vx, and my hypotenuse would be my V. If I multiply both sides by V, I get V cosine theta, which is going to be 15 cosine 70. I go in my calculator, 15 cosine 70 gives me an initial velocity in the x of 5.1 meters per second. And so now we can eliminate that 15 meters per second. It's not really useful anymore because now I know that I effectively have an object moving horizontally at that speed, 5.1, and vertically upwards at 4.1 meters per second. Now from here, it looks like I don't even need the x side. It doesn't ask anything about where it is in the x position. I don't have the x final, so it doesn't help me find time. So I'm going to look on the y side. I have both positions in the y. I have an initial velocity. I have a. So I'm going to find the time in the air using the y side. I think I have everything I need to know. This is really just a one-dimensional problem. And I know that y final is 1/2 AYT squared plus V initial in the YT plus Y initial. And I'll plug in what I have. It finishes at an elevation of 3.2 meters. Half of negative 9.8 is negative 4.9 T squared. The initial velocity is 14.1. It's multiplied by time plus my initial position 0. And now I'm just solving a quadratic. I need to subtract 3.2 from both sides to isolate a 0. And I get negative 4.9 T squared plus 14.1 T minus 3.2. Again, I've subtracted 3.2 from both sides. And you guys would hopefully recognize we have an A, a B, and a C. And I can use the quadratic formula, which I have written up here. T equals negative B plus or minus square root of B squared minus 4AC all over 2A. And I've gone through the process of programming into my calculator to make my life easy. Again, it's just a tool to solve problems. The physics is knowing how to apply the tool. My A is negative 4.9, my B is 14.1, and my C is negative 3.2. And I get 2 times. I get T is positive 0.25, 0.25 seconds, and positive 2.63 seconds. I get 2 positive times. And when we solved problems before, we know usually if you get a negative time, you could throw that out. But in this case, we got 2 positive times. And now it's our job to interpret, well, which one is it? And let's look at what that really means. When we do the math, we're looking at a parabola. And we're asking, hey, when is it at a position of 3.2 meters? When is the object located at this height? Well, if you look at your parabola, it occurs here and at the hole. And so we get 2 times. The first time, 0.25 seconds, is on the way up, passing. And in order for that ball to actually go in the hole, it would have to be striking the hole on the way down. And so this is going to be the time on the way down, which is the time that we want. So that's our answer for the first part of the question. So the second part asks, well, what angle did it strike the cup? Now, in order to find an angle, we need to know what velocities it hits the cup. So if I break this thing up, here's the cup, here's my pin. This object is coming in with a velocity V final and strikes the cup. And it's going to hit it at this angle theta. That's what I want to find. Now, in order to find that, I need to find my component pieces of that final velocity. And we know that it's going to have some component that's downward. That's going to be the final velocity in the y. And it's going to have a component piece that's horizontal. That's my x velocity. And so in order to find the angle, I need to know what v final in the y is. So I'm going to find v final in the y. And if I look at my equations up here, v final equals at plus v initial. Well, I now know the time to the cup, 2.63 seconds. And so v final is the acceleration in the y times time plus the initial velocity in the y. That's going to be negative 9.8 times 2.63, the time to the cup, not the smaller time, plus 14.1. And I'm going to get negative 9.8 times 2.63 plus 14.1. And I should get a negative velocity that isn't quite as big as my initial one. And in fact, I get 11.7. V final in the y is equal to negative 11.7 meters per second, which makes sense. It should be going downward, which is true. It's negative. It's not quite as fast. Had it fallen all the way down to the same elevation, it would be negative 14.1. So it hasn't gained all the velocity back. And so I have a final velocity in the y that has a magnitude of 11.7 meters per second. And I have a velocity in the x that hasn't changed. It's constant. It's 5.1 meters per second. And so if I do a little trig, if I look at my triangle, I have two sides of that triangle. I have the opposite of theta, and I have the adjacent. This is my opposite. This is my adjacent. And the function that has opposite and adjacent is tangent. We know that the tangent of theta is equal to the opposite over the adjacent, which means, in this case, the tangent of theta would equal 11.7 over 5.1. Now keep in mind, my velocity was negative, but if you look at my picture, I've drawn a downward arrow that accounts for that negative. When I'm using trig, I really just care about lengths of the triangle. The direction arrows determine how I draw them. So using the trig functions, you don't have to worry about the negative signs. And if I want to actually get theta, I need the inverse tangent. Tangent to the negative 1 of 11.7 over 5.1. And in my calculator, that inverse function is above the tangent. I do second tangent of 11.7 divided by 5.1. And I get an angle of 66.4 degrees. That would be the angle that that ball strikes the cup. And if I wanted to know how fast the ball is going when it hit the cup, which the problem didn't ask, I would simply use Pythagorean theorem. A squared plus b squared is c squared. So I would square the 11.7, add it to 5.1 squared, then take the square root, and I would know how fast the ball is going when it hit the cup. And I'd imagine it'd be less than 15, because if the object went all the way down to the ground, we know at this point it should be going 15 meters per second and have an angle of 70 degrees, based on some of the things we know about when the elevation is the same. Hope this helps give you an idea of an angled launch projectile motion problem.